In this video, we're going to talk about solving homogeneous linear differential equations with constant coefficients. The method to solve them is very easy, but it can seem like magic if you don't know why this is how you solve them. You can skip ahead if you just want the formula and to see me solve some examples, but first I'm going to try to show you where this method comes from. We start by considering a mass attached to a spring. We pull the mass down, and then we release it, and it begins to oscillate. I'm interested in this block's height as a function of time, so let's make a graph. The horizontal axis is time, and the vertical axis is height, which we'll call y of t. And now we plot its height. We'll include another axis to the right, and we'll represent the height in another way. Now we have the height of the block being represented by this arrow. I also want an arrow to represent the block's acceleration. When the block is at the bottom, the acceleration is pointing straight up, and when the block is at the top, the acceleration is pointing straight down. Let's pretend you measure the acceleration and it looks like this. I'm going to say that it looks like y double prime of t is equal to negative 4 y of t. Before I move on, you may be wondering if the white arrow really represents the acceleration of the block, or maybe how did I determine the white arrow? Just pretend that it does represent the acceleration for the sake of this example. Let's look at the graph from the previous board. Remember, we're interested in figuring out what this function y of t is. It looks like some sort of cosine wave, so let's plot cosine of 9t as a guess. Now cosine of 9t doesn't match up perfectly, but maybe we can modify our function. Instead of cosine of 9t, let's write cosine of omega t. And I'm imagining that we can vary the value of omega, and maybe there's a special value of omega that will give us the right function. How would we know if we had the right value for omega? If our function was y of t is equal to cosine of omega t, if it was the right function, it would solve the differential equation y double prime of t plus 4y of t is equal to 0. Computing out y prime of t, we get negative omega sine omega t, then y double prime of t is equal to negative omega squared cosine of omega t. Plugging this into our differential equation gives us negative omega squared cosine omega t plus 4 cosine omega t is equal to 0, which tells us negative omega squared plus 4 times cosine of omega t is equal to 0. This tells us negative omega squared plus 4 is equal to 0, which then implies that omega is equal to plus or minus 2. Since cosine is even, it doesn't matter if we plug in 2 or negative 2 for omega, we end up with the same solution, which is that y of t is equal to cosine of 2t. We can check this by computing y double prime of t plus 4y of t, and what do we get? We get negative 4 cosine of 2t plus 4 cosine of 2t, which is indeed equal to 0. Let's summarize what we previously did. We had the differential equation y double prime of t plus 4y of t is equal to 0. We saw that the graph looked like some sort of cosine wave, so we guessed that y of t was equal to cosine of omega t. We didn't know omega, so we plugged cosine of omega t into our differential equation, and we found that omega was equal to 2. The actual method we end up using will be less intuitive than this. To get to it, we need to make an observation about cosine and sine. Let's go back to Euler's formula, which tells us that e to the it is equal to cosine t plus I sine t. Now, doing some arithmetic, we can do e to the it plus e to the negative it over 2, and then computing some things out, canceling stuff, we end up getting that this is equal to cosine of t. We end up with the following formula for cosine of t, which is e to the it plus e to the negative it over 2, and sine of t is equal to e to the it minus e to the negative it over 2I. In general, we have cosine of omega t is equal to e to the I omega t plus e to the negative I omega t over 2. Right now, it's not really important to me that you memorize this formula. I just want you to be aware of the following, that cosine of omega t can be written in terms of exponentials, and that's what's going to lead us to solving homogeneous linear differential equations with constant coefficients. We're going to do this example again, but this time, instead of guessing that our function is cosine of omega t, knowing that cosine of omega t can be written as a sum of exponentials, we're going to guess that our function is of the form y of t is equal to ce to the lambda t. And the idea is that we need to find the correct lambda for it to be a solution to our differential equation. We're going to plug ce to the lambda t into the differential equation. We get the following if we compute y prime and y double prime. Plugging this in for y double prime plus 4y gives us c lambda squared e to the lambda t plus 4 times ce to the lambda t. By factoring out the lambda squared plus 4, we get lambda is equal to plus or minus 2I. So there are two values that lambda can be, and our differential equation is linear, so we can construct our solution as a sum to get y of t is equal to c1 e to the 2it plus c2 e to the negative 2it. You may be wondering why this looks different from our previous answer. In the previous answer, we had secretly already imposed some initial conditions, so let's include these as y of 0 is equal to 1 and y prime of 0 is equal to 0. Computing this out and solving for c1 and c2 gives us exactly the formula for cosine of 2t that we previously derived. I want us to go through this example one more time and really look at what's happening. Again, we have our differential equation y double prime of t plus 4y of t is equal to 0, and we guess that our solution is some y of t is equal to ce to the lambda t. We need to plug our function into the differential equation to find lambda. When we computed y double prime plus 4y, we ended up with lambda squared plus 4 all times ce to the lambda t. What I want you to take notice of is this equation lambda squared plus 4. This is going to show up over and over when we're solving homogeneous linear differential equations with constant coefficients. It's important enough that we should name it, so I'm going to call it the auxiliary equation or the characteristic polynomial. There's a relation between the differential equation and what the characteristic polynomial is. Our differential equation was y double prime plus 4y is equal to 0, and our auxiliary equation is lambda squared plus 4 is equal to 0. I've written lambda to the 0 in place of 1. And you can look, so there's two derivatives on the first y, and there's a squared on the first lambda, and there's 0 derivatives on the next y, and there's a 0 power on the next lambda. The roots of the auxiliary equation were lambda is equal to plus or minus 2I, and these roots told us that the solution was y of t is equal to c1 e to the 2it plus c2 e to the negative 2it. Now I'm going to show you the general method to solve any homogeneous linear differential equation with constant coefficients. That's a lot of vocabulary words, but they're things like y double prime plus 4y is equal to 0, or 7y triple prime minus 6y prime is equal to 0. In general, they're anything that can be written like this, where each of these a sub n's are constants. The general method is that you imagine your solution is of the form y of t is equal to ce to the lambda t, and if it was a solution and you plugged it into the differential equation, you would get the auxiliary equation. The roots of the auxiliary equation are going to tell you what the solution to the differential equation is. When you factor the auxiliary equation, it'll be written out something like this, where the r sub i's, these are the roots themselves, and then the power is the multiplicity of the root. As soon as you have the auxiliary equation in this form, you can pretty much just read off what the solution to the differential equation is. Here I'll write out the formula in general. You can pause and memorize this formula if you want, but after I do a couple of examples, I think you'll get the idea of how it works. We're going to have these e to the r sub I t terms coming from each root, but then we also have to account for the multiplicity by adding in these terms where we multiply by t raised to some power. Don't worry, I'll do about 4 examples. For our first example, we'll start with something easy. So let's solve, in general, any first-order homogeneous linear differential equation with constant coefficients. And this is just anything of the form ay prime plus by is equal to 0. And we'll go through it step by step. So first, we're going to write the auxiliary equation, which in this example is a lambda plus b, which is equal to 0. And then we need to find the roots of the auxiliary equation. And here it's lambda is equal to negative b over a. And then the general solution to the differential equation is y of t is equal to ce to the lambda t. As an example, let's pretend our differential equation is y prime minus I times y is equal to 0. Then the auxiliary equation is lambda minus I is equal to 0, and this has root lambda is equal to I. And our solution is y of t is equal to ce to the it. I included this example because I use this differential equation when deriving Euler's formula, so maybe now that you've seen this, you can go back and re-watch that and have a better appreciation of it. Now we'll do a second order with distinct roots example, and these are equations of the form a y double prime plus by prime plus cy is equal to 0. Again, we follow the same algorithm. We're going to write the auxiliary equation, which in this example is a lambda squared plus b lambda plus c is equal to 0. We can use the quadratic formula to find the roots, and let's call them lambda 1 and lambda 2, and we're assuming they're distinct. That's very important here. Then the general solution is just the linear combination of the exponentials, so it's y of t is equal to c1 e to the lambda 1t plus c2 e to the lambda 2t. As our example, we'll do y double prime minus 5y prime plus 6y is equal to 0. Our auxiliary equation is lambda squared minus 5 lambda plus 6 is equal to 0. We can factor that into lambda minus 3 times lambda minus 2, which has roots lambda is equal to 2 and 3. Then our general solution is y of t is equal to c1 e to the 2t plus c2 e to the 3t. Now let's do an example where we have to account for repeated roots. So again, this will be a second order equation. It's something of the form a y double prime plus by prime plus cy is equal to 0. Again, we find the auxiliary equation. We get a lambda squared plus b lambda plus c is equal to 0. And we find the roots using the quadratic equation, but this time we're going to assume they're repeated, which means the discriminant is 0, but anyway, we only have 1 lambda this time. Now the general solution looks like this. We have y of t is equal to c1 e to the lambda t, but we also have to include a term of the form c2 times t e to the lambda t. Our example will be y double prime minus 4y prime plus 4y is equal to 0. Our auxiliary equation is lambda squared minus 4 lambda plus 4 is equal to 0. This factors into lambda minus 2 squared is equal to 0, which has a repeated root of lambda is equal to 2. Then our general solution is y of t is equal to c1 e to the 2t plus c2 t e to the 2t. Okay, as our last example, we're going to do some crazy differential equation. I'm not even going to say it, I'm just going to write it out. And just trust me that whenever you wrote the auxiliary equation down and you ended up factoring it, you would get this. You would get lambda minus 2 cubed times lambda plus 5 squared times lambda minus 7 times lambda plus 3. Now, this seems like a really complicated differential equation, but we can just read off the solution from the roots of the auxiliary equation. So our solution is going to be y of t is equal to, let's look at the lambda minus 2 term. The multiplicity is 3, so we have c1 plus c2t plus c3 t squared all times e to the 2t. That takes care of that part. Moving on to the lambda plus 5 term, it has multiplicity 2. So now we have c4 plus c5 times t, all times e to the negative 5t. Next we have the lambda minus 7 term, which has multiplicity 1. So this is just c6 e to the 7t. And finally we have the lambda plus 3 term, which again has multiplicity 1. So now we just add c7 e to the negative 3t. And with that, I'm going to end this video.